Looks like we still have a few more people to come in, so it's great to see so many people. I don't know where we're going to see everybody, but my name is Mathew Lodge. I'm CEO at Diffblue. Diffblue is an Oxford University spin-out, and we make software that writes software. So what we're going to cover today, we're going to look at the generative AI for code landscape. When I first joined Diffblue in 2019, and in 2020, we tried to convince the Wall Street Journal they should write an editorial. We wrote them an editorial about how software was going to write itself. And the editors of the Wall Street Journal were pretty skeptical that this would be a thing. I don't think we would have that problem today, right? It is one of the hot spaces. We saw the announcement of GPT-4. ChatGPT has democratized access to this kind of technology. So let's look at the landscape. We're going to look at large language models. We're going to spend quite a lot of time on LLMs because they are the latest and greatest technology. We're going to look at coding suggestions using large language models. And then we're going to look at reinforcement learning and the role that that plays and how that's a different approach to generative AI. And we'll have a live demo because there is nothing like doing a live demo, right? All right, so ChatGPT is cool. I asked it to write a haiku about a late software project, and it did, and it wrote a good one, and it had the correct number of syllables in all of the lines and everything. You've all heard of the Turing test. This is the Turing-Ramsey test. Explain why my software project is late in the style of Gordon Ramsay. And it got the first line is late because you're a donkey. So those of you who know Gordon Ramsay, I thought this was pretty good. This is Bard, Google's large language model. And then I asked Bing Image Creator, which is a version of DALL-E, to do me a picture yesterday for this talk of a man learning to play basketball by reading a book, which might seem like a very cryptic thing. I thought it did a great job. This court is a little trippy here at the back. But we're going to come back to this idea. Can you learn basketball by reading about it? Because that is the essence of large language models. So we're going to come back to this idea. So we think about generative AI for code in terms of the state of the art today. We got things like GitHub Copilot. So on the back end of Copilot is a version of GPT. Tab 9 predates Copilot by a few years, actually. They started out on GPT-2, and they have evolved their own proprietary model at this point. And of course, you've all seen examples from ChatGPT. And then on the unit test writing side, rather than code suggestions, you've got reinforcement learning. So we got us, and there's an open source project called Evo Suite. It uses a very similar technique. So we're in contrast to the transformer-based large language models. So transformers are the core technology behind large language models. So Google first developed the transformer, Google research team, and they were interested in things like machine translation. And so a transformer is trained on a text. In this example here, we're doing English to French, and so this was trained on sentence pairs, right? So you've got the English sentence, you've got the French sentence, and you've got millions and millions of these pairs, and you train the transformer. It's a form of neural network. It's very similar to a lot of the predecessors, things like image recognition neural networks. But the transformer architecture, which you can read more about in the Google paper, it's called Attention is All You Need. The thing they did differently with transformers that they hadn't done previously with language models was to be able to break up the input into tokens. Now, token pretty much corresponds to a word in language models. And you want the model knows, the tokenizer knows what part of speech the word is. So it knows if it's a noun or an adjective or a verb, whatever. And so that information is used in training of the network and is used in part of how the transformer is able then to predict what the next word is. So the transformer learns statistical patterns of text. And so you can feed in the quick brown fox and you say, what's the next word that I would expect to see in French for this version? And so we say le, and then we feed that output back in through the transformer, and we get the next word, which is le renard, the fox, and so on. So transformers are just iterating on this. So they're just one word at a time. The question that you're asking the neural network is, what's the next word? What's the next token, actually? So pre-trained transformers started out with OpenAI back in February 2019. They were not the first, but they did one of the first open source models. So open source model on data, so pre-trained in the sense that you could get not just the model, but also the data that goes along with that. 1.5 billion parameters, which today, we laugh at 1.5 billion parameters. But at the time, you have to remember that ResNet, which is a neural network that can identify images off of the internet better than humans, was a 0.05 billion parameter model. Right, so these language models were big. And part of the reason they were big is because they were encoding a lot of the source material that they're analyzing. So the reason that Bard knows about Gordon Ramsay is because that knowledge has been encoded into the model. That's one of the reasons why these models are so big. So you can see that GPT-3, when it came out, 175 billion parameters, closed source at this point. But there was a really great paper published at the same time about how the model was built, how it was trained, all of those good things. These models were really interesting. They were able to summarize text. They were able to write new text, answer questions about a text. So really interesting stuff. The ability to make stuff up, like my haiku, is a real key strength, actually, of this kind of technology. So building new content, copywriting, blog posts, social posts, things like that. GPT 3.5 came out in November 22, also closed source. Very similar to GPT-3, but with the addition of some reinforcement learning on the back end, and I'll get into that in a second. So they call that reinforcement learning with human feedback, and I'll explain what that means. And you could write code with these, and Codex, which was the original model that was behind Copilot when it first launched, which they have since retired, was about a 5 billion parameter model that was specifically trained on open source. So just to give you an idea, 175 billion parameter model, to train that thing, it's 3.14 times 10 to the 23 flops to train. So 355 GPU years on the fastest available NVIDIA GPU today. They've announced some new ones that are a little faster. But essentially, you can sort of get an idea from this how big these models are and how expensive they are to train. This is not a business you can get into with typical funding you would expect for a startup. This is something where you've got to have billions in the bank in order to be able to do this. Of course, they don't train this on a single GPU. I was just trying to give you a sense from this of how big it is. It's trained on a cluster because, for one thing, the model doesn't fit in memory of a single GPU. So they have to segment it and train it that way. It's trained on Azure GPT. And here's what we know about GPT-4. It's a black box. So they've decided not to tell us anything about the model, how big it is, how it was trained, any of those things, which I think is really unfortunate because the development of this space has largely been about people building on other ideas, right? This whole OpenAI would not be able to build something like this without the original Google work on transformers, for example. So we don't know how big it is. There's some guesses. There was somebody who said it's 1 trillion parameters. I don't know if that's true or not. Nobody knows. I guess only the people at Microsoft know. So if we think about these models, though, they really were remarkable. And they were remarkable for 3 reasons. The first one is that they were very, very accurate in one shot. Right? So you could give it a prompt, and it would do a very, very good job just on a single shot. It wouldn't have to refine that. You wouldn't have to keep feeding things back through, which is, again, different to some of the previous approaches. And it does text generation tasks that it hasn't been explicitly trained to do. And that was a really important distinction, because if you think about image recognition, those were very specific to the images they were trained on. So ResNet that I mentioned earlier was trained on images off the internet. So you can show it a picture of Grumpy Cat, and it says, this is Grumpy Cat. There was a version of ResNet that was trained on X-rays and MRIs, chest X-rays, and it could find cancer. So you could train it on cancerous, non-cancerous images, and it got very good at detecting cancer, really terrible at detecting internet memes. Right? You could show it Grumpy Cat, I had no idea. So the ability to generalize like this was a big deal. And then the third point is that when it was generalizing like this, it could do it with an accuracy that was comparable to an explicitly trained language model. So that was really interesting. You didn't have to have a specifically trained model. It would generalize, and it was just as accurate. So those two things together were pretty interesting to lots of people, especially if your mission in life is to build artificial generalized intelligence. Because now you have something that generalizes. You don't have to explicitly train it. And so everybody's like, aha, we can have full AI, our future robot overlords. I don't think that's true. But that's one of the reasons why you see OpenAI and other organizations really pushing hard down this path. Some people believe that's where they're going to end. I don't know if that's true or not. But let's get back down to earth. Let's look at code. So here's a really good example of what this technology can do. This is for a boilerplate. So you can see right at the top of the screen there, this might be a little difficult to see in gray, but there's a comment that says, I want a person class with a name and age accessors equals and a hash code. And then you start to type the Java for creating a class, and the auto-completion is given right there. And it does a very good job with that autocomplete. It's a really nice boilerplate. That comment is super important at the top, as we will see. Here's another example. This is in Go, and this is for calling the Twitter API. Same kind of things. The kind of thing where you would like, OK, I don't call the Twitter API very often, so let me Google for some code, maybe search Stack Overflow, find some examples. It gives you basically a full example in an autocomplete. And again, it does a very good job. So this kind of stuff can be really useful, and it's comparable to going on Stack Overflow. So one of the nice things about the original GPT paper is that they looked at where it didn't do so well. And what's interesting about the shortcomings is that they are very consistent over time. There are papers that predate GPT-3 looking at transform architectures and point out the same thing. As we will see, GPT-4 has the same weaknesses. And the first one, ironically enough, is drawing factual conclusions. This is technology that everyone is telling you is going to replace Google search, right? You're just going to be able to talk to ChatGPT and it will tell you the answer, except that it's not very good at facts. And so this has presented a challenge. We'll talk about some of the ways to try to solve that. But these models have their weaknesses. It means they're very good for some things. They're not so good for other things. Right now, you would not believe that from the hype, where the hype is like, they can do everything. This is the future of general intelligence. But that's not the full story. I think they're being oversold to a certain amount. Multiple digit maths, OpenAI did a really good analysis of the accuracy. Basically, the more digits, the less accurate it is. They also looked at the effect of model size on the accuracy for maths, and it's not pretty. It doesn't get better. And that's part of the reason for that is this is a language model. It doesn't know anything other than statistical text patterns, and that's what makes logic and maths and things like that quite difficult. Repetition, lack of coherence, what I call losing the plot, is a challenge. It's still a challenge for GPT-4. And fundamentally, because these are statistical models of text, small prompt changes can make an enormous difference in the outcome, and it's very difficult to know. There are people who claim you can do this thing called prompt engineering, and to a certain extent, there are some rules of thumb about how you construct a prompt to give the model more information. Beyond that, nobody knows. It's not really engineering. I would not call that engineering. It's guesswork. So it's a statistical model of textual patterns. By the way, I do want to have a show of hands. How many people know who that actor is? OK, all right. I'm getting old. So that's Yul Brynner, who was a big deal when I was a kid. Right, GPT 3.5. So for unit test writing, so this was our world. And so we were like, hey, this stuff looks pretty cool. Can it write unit tests? So we spent quite a lot of time of looking at, how well does it do? How good is it for unit test writing? So I'm going to show you some examples here that sort of illustrate some of the challenges. And here's an add method that's got nothing in it. And the unit test it generates is great if only that method added something. So what's going on here is it's keying off the text. So the text is super important to these models. It doesn't know what your program does. It knows what it says it does. GPT-4, by the way, makes the same error. Right? This is what GPT-4 generated for the same example. It's more verbose. looks nicer, wrong, confidently wrong. And that's part of the pattern for large language models. If we write an add method that multiplies, same kind of thing, perfectly reasonable test if it actually added numbers together, but it doesn't. And you might say this is somewhat contrived. Who writes an add method that's got multiply in it? Absolutely true. You wouldn't write something like that. That kind of thing is unusual. The reason I'm showing you this is because it illustrates how the models work, how to get the best out of them, and where they can go wrong. And then here we have an example of losing the plot. We talked about this as a challenge. So this is a saturating add. You can add the two numbers together, and if the result is bigger or lower than the threshold, you just return the threshold. And you can see that in GPT 3.5, we get a junk unit test that tries to instantiate a thing called date time service that presumably it saw in some code somewhere, but is not a method that exists for the calculator. So the other thing that's in GPT 3.5 is humans in the loop to tune the algorithm. So one of the problems with not giving factual answers is, well, maybe we can have some humans take a look at this and tell it when it makes a mistake. So here's an example for Citizen Kane is, and then we're looking for the completion of that. And so these are all things that were said about Citizen Kane, the movie, one of the greatest movies ever made, arguably. I would argue it is. A commercial failure, that was true. William Randolph Hearst, who was the target, the person being lampooned in Citizen Kane, pretty successfully shut the movie down. It was the end of Orson Welles' Hollywood career. He never made a big Hollywood movie after this. And it was also said that it was a vicious and irresponsible attack on a great man. So one of Hearst's friends said that. Essentially, they take all of those answers and have humans rank them. And so if you've ever used ChatGPT and you've got that little thumbs up, thumbs down thing, this is you doing the ranking. So they take that and they feed that back into the model. But a lot of work was done mostly in the Philippines, so basically large-scale crowdsourced rating of answers from the model in order to tune it. Did a similar thing for they have a safety filter to try and stop it from saying racist things. You can prompt it into being quite offensive. And so they tried to put in a filter to do that. I say tried because there were numerous examples of people breaking that filter very easily. But essentially what they're trying to do is use humans to tune the output of the machine. And this is also why, if you've seen an example where GPT-3 didn't do very well on a particular prompt or a particular example, and GPT-4 does a much better job, this is why it's been trained. Pretty much all of those examples that have been published have been trained into the model. So here's an example for coding. I said, write me a Python function for a perceptron, which is a fundamental building block of neural networks. Now, nobody's going to pay me to write code these days. I used to be a developer years ago. But I can spot 2 bugs in this code. There may be more. So the first bug is that it sets the weights to 0. This perceptron will never learn. Because right down here at the bottom, we multiply by what's in the weights array, which is in X by that point in the Python program. That's always 0. So the answer is always 0. The learning doesn't matter what the learning rate is or any of those other things. It will never learn. The other thing that it doesn't do is normalize the inputs for training. So people who are real data scientists and actually write Python code to do machine learning for a living tell me that you always normalize the input vector so that you don't have features on different scales having different effects on the model. You want everything to be normalized into the same scale, otherwise it won't learn properly. So you can see that some of the challenges here is like, this looks very good, and it looks quite plausible. It's using NumPy, which is like the thing in Python for doing numerical methods, fast matrix math and all that good stuff. But it's got some subtle bugs, and you have to look quite hard to find them. And then finally, we have an example of GPT misinformation. So this is where ChatGPT generated hallucinatory Python code to call an API to get mobile phone geolocation. That's a company called OpenCage. It's a German provider. So geolocation is to go from GPS coordinates to street address or from a street address to GPS. They have never made an API that gives you a phone's location because that sounds scary and dangerous and private information. And they've never done that. But ChatGPT said they did, gave people code to do it. So they saw lots of signups, and then they saw lots of bad reviews and lots of cancellations. They have no idea why. They'd never said they did this until they found out that you could get that out of ChatGPT. So it sort of gives you an example of how this can go wrong. So the thing to remember is that it's all about the text. So what really matters is the text in the prompt and the text in the training. So whenever you hear someone talking about LLMs reasoning, LLMs don't reason. They just know about text patterns. And that's their greatest advantage. And like all of us, our strengths are our weaknesses, right? So it's the greatest strength and it's the greatest weakness of this approach. There's nothing wrong with understanding that because it helps you get the best out of something like this, but it also helps you avoid the worst. So hallucinations are the term for when training is thin and not enough text. People have been writing papers about hallucination in this kind of network for years. This is not new. It does not go away. The model gets bigger. It still happens. And another important point is it will never write text that has not been encoded in training. So in code, it will never write any code that calls your internal libraries because it's never seen them. It doesn't know what they are. It's not in the training corpus. It won't generate code that calls them. And these problems are consistent regardless of the size of the model. So this is a technique that has enormous strengths. But as Jeff Hinton from Google pointed out, it's not the only way to learn. Right? We learn to throw a basketball so it goes through the hoop. We don't learn that using language at all. We learn it from trial and error. So the guy on the left is not learning how to play basketball. The woman on the right is learning how to play basketball. And so, Jeff Hinton is one of the people who invented backpropagation. He's like OG machine learning guy, right? He really knows what he's talking about. And the point is that there is more to life than large language models. And it's, to a certain extent, a matter of horses for courses when it comes to algorithms. So that brings me on to Diffblue cover, because we do reinforcement learning. Surprise! Which is a bit like learning to play basketball by trial and error. So what does that mean? So when we write code, we write unit tests for Java applications at Diffblue. You can think about coding as a form of search. Essentially what we're doing is conducting a search of this set of all possible programs for tests that are valid and run, that get high coverage, and that developers find easy to read. So using reinforcement learning for search is not new. It's the basis of a lot of game-playing AI, so things like AlphaGo, and some of the early OpenAI stuff around Dota, where they were building adversarial networks that were very good at playing Dota. Consistently accurate test writing is much harder than code completion, because the accuracy part is the hard part, and being able to do that consistently. So the large language models are trading accuracy to be more general. So that's their strength. They can support they can write code in lots of different languages, for example, but they're not as accurate, and that's why they need human supervision. So when we're writing text, we need tests. We need a lot more context. We need a semantic model of the program. We have to have some idea of what the code does. And this is most valuable when it's 100% autonomous. Some of our customers run our product against million-line Java programs. They get tens of thousands of tests on a single run. It's not scalable to have humans generate a test, figure out where the bugs are, edit that themselves for that kind of scale. So in terms of reinforcement learning, how does it work under the covers? Essentially what we do is we write a test, we run it against the method under test, and we see how it does. We see what coverage it gets. We have other information about the program, including what the existing code looks like. That's some of our secret sauce, if you like. From that information, we're able to predict what a better test looks like, and we run that, and we see how it does. And then we repeat. So we're iterating, we're trying to improve the test every time. Sometimes the test gets worse, and essentially you want to backtrack and try something else at that point. But essentially, you're conducting a search of possible test programs, and we keep doing this until we've got test programs that maximize coverage. So fundamentally, that's what the product is doing under the covers. And so as a result, for unit testing, if you think about a typical change process for software, these tests are most useful for detecting regressions. So right, you write a code change, you create a pull request. As part of the pull request, you run the unit tests. So a CI might run that for you. And then, if tests fail, you take a look and try and figure out what's happening. Do you need to fix the test? Do you need to fix the code? Until you're happy and the PR is approved. And so with Diffblue, you can have the product write a unit test baseline, so write a set of tests for the entire application. And so those tests can be run along with any test that you've written when the pull request is run. And I say relevant tests only because we have a nice little test optimizer in here. For any given PR, we can tell you which tests will reach that code because we understand what the call graph looks like. So we use this ourselves. It saves us about 50% on our CI costs because we only ever run the relevant tests. Failing tests tell you about problems, potential problems in the code. You can update those, or you can have the product do the update for the tests. So you get the new tests directly from that. We can generate new tests that are relevant to this particular PR incrementally. Right, so let's try a live demo. If I can. The joys of live demos. Hello. There we go. All right, so I had a bit of a heart attack there. I've fallen at the first hurdle. Right, so I'm going to run Pet Clinic. For those of you, who's seen Pet Clinic before in the Java world? Okay, yeah, fair number of people. All right, so Pet Clinic is an example application for Spring Java Framework, fictional vet's office, and so I can do things like find the owner, and it gives me a nice paginated list of the owners. And I can do a search for a particular owner, so I can say, what about me? I don't have any pets, so I'm not found. So there's a bunch of things here. So what we're going to do is we're going to take a look at the code for that. Before that starts, what I'm going to do is we're going to run Diffblue cover. So this is going to take about 1 minute, 30 seconds. I'm going to set this off going, and then we're going to come back and look at the results. So what it's doing right now is figuring out the Java environment, JVM, and so on. So if I switch back to Pet Clinic, that wasn't found. So that's one of my other test cases. Then if I put in Davis, there are 2 owners, so the name Davis, so I get a list of owners. I can choose the one I want. And then one of the other ones I can put in here is I can put in a single owner, McTavish. In the case of McTavish, then we get a nice little optimization. It doesn't give you a list with one owner in it. It just takes you straight to the record for that owner, right? So we've got 4 test cases there, right, for this application. So if I am able, let's see if I can do this through this scary blank screen, to this, when you look at the Java code, then we can see there's 4 cases, right? So we've got empty field, find all the owners, not found. And we need to put that message there, send you back to the page to find, the search page. Exactly one result. Then we go straight to that owner, and then 2+ results. Then we get paginated list. So it's easier just to show you that on a slide versus trying to show you in an IDE. So what we're going to do is switch back to the terminal. And there we go. So we've created some tests. 1 minute, 20 seconds. That's right, this entire thing ran locally, by the way. This is running on my laptop. There's no cloud service or anything like that. So it runs directly on your code. And then I'm going to switch over into IntelliJ so we can go look at the code that's been written. You can see that a new file has showed up. So I'm going to control a Diffblue test. And so this is the code that has been written by Diffblue. And here is the code that we have written, starting here, for those 4 test cases. And so the first example, we just create an empty list. We want to see that we end up back at fine owners. So we've got a mock here. We're mocking out the database. We don't really want to go to the database to run this query because we want to run it quickly. So we have a when-then where we return the empty list. We mock a request into the Spring controller, and we look at the result that comes back, and we say we expect that it should work, it's OK, and we should expect that the owner attribute exists, and we should expect that the view that we go to is find owners. Right? So that's the empty case. Here's what happens when we do the single owner case. So first of all, you see that we've written a test where we're creating an owner. We need to create an object of type owner, again, for mocking purposes. We're not going to the database. We're going to return this. So create an array, add the owner to it. There's our owner list, and then we can do the mock and say return that single owner, and that gives us the ability to check out the logic for single owner return. And if I can scroll, there we go. There's the magic line. We get redirected to owner 1. ID 1 that we created earlier. And then, as you might expect, for the next version, we create 2 owners and we put them in an array and return both. And we check that we end up in the right place. So there we are. And then finally, we have the 4th case, where empty array list, and we put in doe as the name, and that won't be found. So we've got the negative case. So that's an example of what you can do with reinforcement learning. So all of this has been generated by us trying to find a way through this code and constructing objects and essentially iterating on various different versions of tests to come up with this. So that gives you an example of how that works. So it's a very different method. It is the basketball method. All right, we're taking shots on the hoop and finding out which ones go through. And so it's great. The limitations are that it's great and autonomous for Java. We don't support any other languages today. We will do more in the future. Kotlin is the next language we will do. It's 100% autonomous. Because we are the method that we're doing, we're running the test against the code all the time, then we know that this code is correct and it runs because we ran it. And we know what result it gets because we've been able to observe that when we ran it. We also validate all the tests at the end. Right? So we run the build. You saw the message if you were looking at the output. We run the test just to make sure that nothing is going to fail, because you want your unit test suite to pass. Right? That would be bad if it did not pass. And then there's a dashboard, which I won't show you, for coverage, testability, risk, and so on. And so the net generative AI for code tools can help you eliminate that tedious and error-prone coding. I told you about the 2 different ways that this works. We've looked at large language models, which are very good for things like boilerplate, very good for calling into foreign lands, but are not accurate. And then reinforcement learning is just much better for unit test generation. And we have the numbers to prove it. You can try all of these things for free. There is a free community edition of Diffblue cover that you can get from the IntelliJ marketplace. So if you use IntelliJ, you can just install it. There's also a free trial on the website. You've got the QR code for the link there. There's a CI integration. There's a CLI version. So if you don't use IntelliJ, or if you want to try the command line, you can try that. Just put your name and email in. We will send you a license. And that's the end of my presentation. Thank you very much. Right, we have time for Q&A. So, Julian. Yes.
So from my understanding, you are generating these tests based on existing code.
Yes.
So,
thank you.
Thank you.
There we go.
I'll just repeat that. From my understanding, you're generating tests based on already written code.
Yes.
Therefore, you're relying on the developer to actually interpret the specification correctly. Do you have any plans to actually generate tests based on some sort of specification so that tests actually fail if the code doesn't meet that specification?
We don't. Part of the reason is that we've yet to come across somebody who has any of those specifications. It's really hard to build a product for a thing that doesn't exist.
Cool, thank you.
I'm slightly flippant there, but that is a real challenge, whereas we have lots of customers who don't have much in the way of unit tests and have lots of code. So for a small company, it's prioritization.
Thank you.
Thank you. I think I got, oh, sorry, we'll get to you.
Hi.
Hello.
So you talked about the problem where there's an add function that does multiplication and it's
Yes.
called add. And does Diffblue read, for example, the function names and figure out that this is doing the wrong thing? Or would it fall in the same problem that ChatGPT would fall for? We're writing unit tests for that.
So no, because we only know what the code does, not what it says, right? So the method of writing a test and then running it and seeing what happens, we learn what the code does through observing the behavior. So we don't care what the text is, we just care what it does. And from that, we can determine what the unit test should be.
All right, thank you.
Yeah.
I've seen on the demos that the naming of the test is generic.
Yes.
You have a plan to give it a more descriptive names?
Yes. So there's one of the drawbacks of the approach is that it's not easy for us to generate descriptive names. So we've tried feeding that into a large language model. Like, what's a good name for this test? And it is surprisingly bad at that, it turns out. And so it is on our roadmap. It's a difficult problem to solve. It's much harder than it looks. We ran a hackathon also at the end of last year, and that was one of the hackathon tasks for our engineering team. So we've experimented with a couple of different things. Unfortunately, large language models don't help us. Otherwise, we would use it. So yes, they are rather generic, and that is a limitation today. Yeah.
Hi, thank you for the talk. One of the questions that I had was, have you considered, well, like a lot of developers use test-driven development to kind of like get out the specification that they want. Is that something that you and your team have considered as kind of flipping it on, where if I have a suite of tests, I have a spec, and could theoretically an application be generated from that, because if that is your requirements at the end of the day?
Yeah, so for test-driven development, there's a couple of different things. So we looked at that. It's a lower priority for us because we found there are more people with lots of code, no tests, rather than lots of tests, no code. And there are LLMs in their current state are not good enough for this right now, but that might change in the future. And we have sort of halfway house where we can write you a skeleton test for a method, and we can give you mocks and things like that, but you have to fill it out. So we can help you write the test in the first place, and at least give you some of the boilerplate for that. But it's not a great answer for test-driven development, and we really are focused on people who have lots of code and no tests. Yeah. Who's next? Gentleman at the back there.
Hello.
We'll get to you. It's okay.
So someone from New York Times said that ChatGPT is an excellent bullshitter.
Has what, sorry?
Someone, journalist from
Yes.
New York Times,
Yes.
said that ChatGPT is an excellent bullshitter. So we should always verify what it's saying. So should we verify also the output of your test, especially if we have a large code base
Yeah.
that dates to 20 years ago?
Yes. Okay. So, New York Times journalist says that ChatGPT is what, bullshit, right?
Excellent.
Yeah. Okay. And should we check the output of your test? You should absolutely check the output of our test. And so when organizations, people evaluate our software, one of the first things they do is spend a lot of time looking at the tests that we generate to make sure that the tests are something that they would like, they're readable, they do something useful, all those things. And once they've satisfied themselves that that is what is happening, then they're ready for large-scale test generation. So they tend to look at a sample, they pick a project, and they do it that way. Yeah.
Hi there.
Hello.
You've emphasized you're kind of targeting organizations with lots of code and few tests.
Yes.
Is there a situation where actually kind of do the test generation, look at what's been generated, and then make a decision, actually, these tests are better than the existing tests that are here, and it will scrub those tests out? Also, actually, we can't improve upon the test coverage here.
Yeah.
While most of the code is generally not well tested, this unit is actually, or this source tree is actually well tested, we can't improve upon it, therefore we're not going to try and add superfluous tests.
Yes, so essentially the reporting application gives you that information. So we'll show you a chart, we'll show you test that Diffblue generated that you didn't, your existing tests, and what the intersection of the two is. And if we can't, you'll see from that exactly how much of improvement or not improvement. So Pet Clinic is the example, is that out of the box, Pet Clinic has great coverage, right? It's an example application, so it's beautifully unit tested, right? And we can't improve on it. We get 96% coverage on Pet Clinic, but you already had 96% coverage from the Spring guys already did that. So you get that from the reporting application. All right, this gentleman here has been very patient. This gentleman here, in the back row. Oh, yeah. Thank you.
Did I understand that you will generate unit tests that only pass?
Yes, that's right.
But if there's a bug in the code,
Yes.
your unit test is just, it's not finding the bug.
Right. So if you think about unit tests in your average application, that's what humans do too. All your unit tests pass. I guarantee it, right? In CI, all your tests pass. And they reflect the current behavior of the program, whether that's right or wrong. Because one of the biggest things you want your unit tests to do is find regressions. You can, at the time of writing, sometimes have a unit test that finds an error that you made. However, because of the way the human brain works, it's actually quite unusual. Because if you wrote the test, the chances are you wrote the code, chances are the two are going to agree. And it's just the way our brains work. It's a human failing. So the value here is in regressions, because that is what unit test suites do when they're written by humans. They help you find regressions for the next PR. Yeah. Yes. A few more.
Hi.
Hello.
Have you made some pull requests to open source projects with your tool, and then so the open source project they get a lot of coverage? So
Yes.
and as you know, so maintaining tests are costs. So
Yes.
our open source project evolve with that.
We've had mixed results. A lot of open source projects, if you're a brand new committer who's never committed anything to the project before, they're pretty suspicious, even if you're committing unit tests. And so we've made submissions to open source projects where they just sit and nobody ever accepts them. We are happy to work with any open source project and give you access. We'll be very happy to do that. We're big supporters of open source. We run our own open source projects. But that has been a real challenge. Okay. Any more questions?
Hello?
Yes.
I would like to ask how you deal with untestable code.
How do we deal with what, sorry?
Untestable code.
Untestable code. I'm glad you asked. So it depends why the code is untestable. So again, our reporting tool will tell you about untestable code, where it is, all the rest of it. We have some built-in automated refactoring. So there are common reasons why why code is untestable. For example, they don't have the right observers. They don't have the right constructors. You can't reach the state inside of an object. So we can't write assertions. For all of those common errors, there's a built-in refactoring tool in the product. You can have it create all the observers for you, and we can fix up that low-level stuff. We hope to expand that in the future to start tackling some of the bigger code testability issues. But our goal as a company is to automate tedious, error-prone stuff. And we think refactoring for testability is one of those things that we can help with. So we'll do some out of the box, but in some projects, there's no getting away from it. You're going to have to refactor, particularly if you've got very long methods where very complex objects. You know, we've seen applications, real-world applications, they've got objects that have got 500 elements. You have to construct an object with 500 elements in order to find a test. And so all those elements have to be correct with respect to each other. The chances of us finding that are slim. And so something like that, breaking it down, refactoring it, turning it into smaller chunks would make it more testable. And there's no getting away from that. Yeah.
Yes.
Yes. Hello.
My question is, the tests are generated and are written explicitly, and perhaps we might generate lots and lots of test code.
Yes.
Given, and perhaps it would be too tedious to go over every one of them.
Yes.
I was wondering if there's a way to identify which tests are really relevant, which lead to inconsistencies, which lead to bugs, and just trim the tests to that.
Yes, so that is what we try to do, actually. We try to give you the smallest set of tests that achieve the maximum coverage and find bugs. So coverage is not the only goal, it's one of the main goals. But for example, we will feed boundary conditions into a method. So we've already got coverage for that method with data that is more normal. We will also feed in boundary conditions. We'll do that because it helps you flush out bugs. It helps you flush out off-by-one errors, things like that. So the product does that by default. Right? That's the default mode. Because early on, we didn't have that capability. We generated too many tests, and people didn't like it for exactly the reason you say. Right? It's too overwhelming. Yes.
My question is, so does the code just mock methods, classes, and all of that, or does it use the, say, Spring framework has a lot of test libraries and stuff, right? So, like mocking out data sources, right?
Yeah.
So Spring has, for example, Kafka.
Yes.
There's Spring Kafka test framework that is available to do this, write these unit tests.
Yes.
So does the code actually use those frameworks, or just simply mock classes and methods?
Okay. So in Spring, we can, as you say, Spring has really great mocking support, and so we can use what's built into Spring framework. Outside of that, we use Mockito, and we'll generate mocks that way. And then the other thing you can do is the static mocking. You can tell, one of the way to optimize the product is you can tell it what to mock. So we allow you to control that manually as well. So we'll do the best we can automatically, and then you can guide it beyond that. Yes.
Hello, thank you for the talk. Do we have any control over the configurations of the test, for example, like the library that we use?
Yes. So essentially what the tool does is it looks at what library you're using, and it uses that. So if you're using JUnit 4, it does JUnit 4, JUnit 5, use JUnit 5, and so on. So it picks that up from the build configuration. Yeah.
Hi.
Yes, hello.
Thank you. Thank you for the great talk. I want to know some of the interesting items from Diffblue's roadmap.
Okay. You should come to the booth. we can talk through roadmap there. Thank you, though. Any more questions? Yes.
So I think my first question would have been something like what she already asked is basically, I'm assuming that at least it sort of looks at how I'm currently writing tests and then it tries to imitate that style in some way. And then the second question would have been, does it do some sort of fixture generating as well? Or is it going to then basically always going to generate me my object, my Pojo class, always in code? And I always basically end up with one large file, let's say, and I don't get, I don't know, some fixtures placed somewhere else.
Yeah, that's right. You can tune it. We give you a feature, you can write your own test harness. So if you want it to write tests in a particular way, or you need a particular setup to make your tests work, then you can tell it manually to do that. And it will do it for everything. Yes?
Thank you for your talk. So if you said that increasing code coverage is one of the main aims, right?
Yes.
How did you get rid of the risk that the model would write like dumb tests just to increase the code coverage?
So we look at the overlapping coverage between tests, and so essentially selecting for the minimal set. And then we have a little bit of data flow analysis to help us, keep the tests that are relevant to boundary conditions and finding bugs.
And is this the same for like making sure that all of the edge cases are covered and everything?
Yeah, the coverage is the main thing that tells us that. And it, if you have good overall coverage, it means you have good branch coverage.
Thank you.
Yeah.
My question is on the coverage. So you try to maximize the line coverage, right? You don't
Yes.
try to compute the execution path, all the passes across all functions and across all the whole application.
I'm sorry, I'm not getting the second part. So we try and optimize line coverage.
So I mean, the coverage that you try to optimize, it's the line coverage or the execution path?
It's line coverage. So because it turns out that everything reduces down to line coverage. It's the most important metric for coverage. All the other coverage metrics basically are the same thing as line coverage.
Yeah, but sometimes you could have some effect, some method calling another method, and if I pass in some branch in the first one, then it might impact the outcome. You see?
Yes, in the same unit, that's possible, and we will find those because we are looking at the behavior of the code. Outside of the unit, that's not unit testing anymore. You're into integration testing at that point. So we're isolating down to a single unit. But if it's in the same unit, we will find that behavior difference and we will write tests accordingly. Yep. Okay. Well, great. Thank you very much. Appreciate it.